Think about a simple everyday situation. You push a box, you pull a suitcase, or you push a lawn mower across the ground. You may feel tired after doing any of these tasks, but in physics, the word work has a very specific meaning. Work is not just effort. Work depends on how a force acts while an object moves. In this video, we will focus on work done by a constant force. The main question is this: when does a force actually transfer energy to an object, and when does it not? To answer that, we need to compare two directions: the direction of the force and the direction of the displacement. If the force points in the same direction as the motion, the force does positive work. If the force is perpendicular to the motion, it does zero work. If the force points opposite the motion, it does negative work. These three cases may look simple, but they are very important because they help us understand energy, motion, friction, and many real world situations. The work done on a system by a constant force is defined as the product of the component of the force in the direction of motion and the distance through which the force acts. The equation is W equals Fd cosine theta. Let us carefully identify each part of this equation. W is the work done by the force. F is the magnitude of the force. D is the magnitude of the displacement, and theta is the angle between the force vector and the displacement vector. The most important part of this equation is cosine theta. The cosine factor tells us that not all of the force necessarily contribute to the work. Only the part of the force that acts along the direction of the displacement does the work. If a force is applied at an angle, we mentally break that force into components. One component is parallel to the displacement, and the other component is perpendicular to the displacement. The parallel component affects the work. The perpendicular component does not contribute to the work because it does not help move the object along the displacement direction. The unit of work is the joule, abbreviated as capital J. 1 joule is equals to 1 Newton meter. So if a 1 Newton force moves an object 1 meter in the direction of that force, the work done is 1 joule. Notice that work is a scalar quantity. It can be positive, negative, or zero, but it does not have a direction like a vector. The sign tells us whether the force tends to add energy to the motion, remove energy from the motion, or neither. Now let us look at the simplest case. In this case, the force is applied in the same direction as the displacement. The object moves to the right, and the force also points to the right. The angle between the force vector and the displacement vector is 0 degrees. Since cosine of 0 degrees is 1, the work equation becomes W equals F times D. This means all of the applied force contributes to moving the object through the displacement. There is no wasted component in another direction. The entire force is parallel to the motion. This is positive work. Positive work means the force is helping the object move in the direction of displacement. For example, if you push a cart forward and the cart moves forward, your push does positive work on the cart. Let us also think about the units. If the force is measured in newtons and the displacement is measured in meters, The work is measured in Newton's meters, which we call joules. For example, if a 10 Newton force pushes an object 3 meters in the same direction as the force, the work is 10 times 3 or 30 joules. The key idea for case 1 is when force and displacement point in the same direction, theta equals 0 degrees. So cosine theta equals 1 and the work is simply force times displacement. Now let us consider the more general case, where the force is applied at an angle. This is common in real life. For example, when you pull a suitcase, your hand pulls upward and forward at the same time. The suitcase may move horizontally, but the force you apply is not completely horizontal. In the equation W equals Fd cosine theta, the term F cosine theta represents the component of the force in the direction of the displacement. If the object moves horizontally, only the horizontal component of the force does work on the object. The vertical component may affect the normal force or it may help lift slightly, but it does not contribute to the work if there is no vertical displacement. Now let us connect this to three cosine values on the slide. If theta equals 0 degrees, cosine theta equals 1. The force is in the same direction as the displacement, so the work is maximum and positive. If theta equals 90 degrees, cosine theta equals 0. The force is perpendicular to the displacement, so the work done by that force is 0. A force can be large and you may feel effort, but if the force has no component along the displacement, it does no work in the physics sense. If theta equals 180 degrees, cosine theta equals negative 1. The force points directly opposite the displacement, so the work is negative. Friction is a common example. If an object slides to the right, kinetic friction acts to the left, opposite the motion. So friction does negative work. This is why the angle matters so much. The same force, magnitude, and same displacement can produce positive work, zero work, or negative work depending only on the angle between force and displacement. Now let us apply the equation to a realistic example. A person pushes a lawn mower with a constant force of 75 newtons. The force is directed 35 degrees below the horizontal, and the lawn mower moves 25 meters across level ground. We are asked how much work is done on the lawn mower by the person. The displacement of the lawn mower is horizontal because it moves along level ground. The force applied by the person is angled downward and forward along the handle. Because the mower does not move downward into the ground, the downward component of the applied force does not contribute to the work associated with the horizontal displacement. The component that matters is the horizontal component of the applied force. The angle between the applied force and the displacement is 35 degrees. That means we will use W equals Fd cosine theta. Now we substitute the values into the work equation. We have W equals Fd cosine theta. The applied force is 75 newtons. The displacement is 25 meters. And the angle between the force and the displacement is 35 degrees, so we can write cosine 35 degrees. And we get W, or the work, is equals to 1536 joules. Now if we round this up to three significant figures, We get the answer 1.54 times 10 to the power 3 joules. Now let us interpret this answer physically. The person applies a 75 Newton force, but not all of that force contribute to the horizontal motion. Only the forward component F cosine theta does work as the mover moves horizontally. Because theta is 35 degrees, cosine theta is less than 1, so the work is less than F times d. Also notice that the work is positive. The forward component of the person's force points in the same direction as the displacement. Therefore, the person is transferring energy to the lawn mower. If we were analyzing all forces on the mower, other forces may also do work. For example, friction would do negative work because it opposes the motion. The normal force and weight would do zero work if the displacement is purely horizontal, because they are perpendicular to the displacement. But in this question, we were asked only to calculate the work done by the person, and that is why we use the applied force from the person and the angle between that force and the displacement. The main takeaway is this: for work done by a constant force, always identify the force, the displacement, and the angle between them. Then use W equals Fd cosine theta. The cosine factor automatically selects the part of the force that is parallel to the motion.